say like, I don't know anything.
Hi everyone, my name is Reagan and I'm a senior data fellow for FSU Libraries. I'm so excited to welcome you all to the first Empowering Minds Through Data Science and Machine Learning Symposium. This symposium is aimed to inspire, educate, and connect students that are interested in learning more about the applications of data science and machine learning. I would like to share with you my intentions behind creating the symposium and why it is so significant to me. There are a lot of conversations going on right now in both university and public settings about machine learning and artificial intelligence and the potential implications that they will have on our lives moving forward. Many students and faculty at FSU are researching new and innovative ways in which we can apply artificial intelligence and machine learning models to probe questions and to make new discoveries. This symposium is intended to highlight some of these exciting projects while also serving as a venue to inspire conversation around these important topics. On a more personal note, throughout my educational experience at FSU, I've absolutely loved getting more involved in research, and I'm so grateful for the opportunities that have been available to me, as well as the resources and support. I hope that this symposium will inspire all of you to get more involved in research and to learn from each other's projects. Today you're going to hear from our keynote speaker, Dr. Jinping Zhang, about his research in large language models and knowledge graphs. And you will also hear from several students who do research here at FSU involving data science and machine learning. You can see the presentation order along with the students' topics in the provided program. And I would now like to thank my FSU Libraries colleagues for their support on today's event. In particular, I want to thank Kyle Wilson from GeoSet, Devin McWhorter from Tech Services, Megan Bonnell and Laura Polini from Marketing, and Crystal Matthews, Elena Faulkner, and Emily McLellan from Engagement. I also want to thank Dean Gail Eschmeyer and the library's senior leadership for sponsoring today's event. And of course, I would like to thank my data fellows and my supervisor, Dr. Nick Rouge, for their invaluable support in this process. After the presentations are completed, please take the time to network and to meet your peers. And also, of course, there's a lot of food, so please feel free to take some. And I would now like to introduce our keynote speaker, Dr. Jinping Zhang. Dr. Zhang is a professor in the Department of Statistics who has done a wide variety of research focusing on computational biology and bioinformatics. Dr. Zhang's research focuses on AI-powered biological text mining and knowledge discovery, as well as understanding the sequence structure-function relationship of proteins. Today, we will be discussing his recent research on creating a large-scale biomedical knowledge graph. This knowledge graph is like a massive encyclopedia with over 11 million entries, all connected by more than 40 million relationships. He's using this knowledge graph to make scientific texts into a more organized and usable form, to allow us to navigate and explore vast domains of knowledge with ease. With this knowledge graph constructed, it can be combined with powerful large language models to address several limitations of current large language models and to take conversational AI to the next level. The title of his presentation is Unlocking Conversational AI's Future, Merging Large Language Models and Knowledge Graphs. Thank you all so much for joining us. I would now like to welcome Dr. Zhang to present his research.
All right. Well, thank you for the introduction. Thank you for the invitation. I changed the title a little bit, but it's still very much related. All right, I will start. Okay, I can move it, right? Okay, I will start with something everybody knows and talk about, ChatGPT. So it's really a revolutionary product, right? And it changed many people's mind and thoughts about what AI is and what AI can do for us. And as scientists, we definitely wonder, can ChatGPT help us with our research? And because that's what we care about. So now let's find out. So that's one of the paper we published in 2020. So definitely before the cutoff date. And in this paper, we discovered a gene called SKR9. And it's important for survival of cancer patients for many different cancer types. And so we published this work. And so I wonder, well, let's ask ChatGPT whether it knows this piece of knowledge. So I say, tell me something about the relationship between SKR9 gene and cancer. And I asked ChatGPT 3.5. It said, oh, I'm not familiar with SKR9 gene specifically. So I know that. Well, maybe it's because GPT 3.5 is not as advanced, but we asked GPT-4. And the same question. And it says, as of my last update in April 2023, well, in fact, you see, that they already used the latest update, right? They just released, I think, this week, right? And then they are, yeah, update time already pushed to April 2023. But still, there's no widely recognized gene by the name of SKR9. And if you actually search SKR9 and cancer, well, at least we can find two papers. One paper is our paper. So indeed, there's something in the literature. But this kind of knowledge is relatively rare, but it's very important, right? Because the latest advancement always just appear in one or two papers, right? If something people talk about many, many times, it's probably not as interesting, right? But this is actually something you want to search, want to find out, because it's frontier, not many people have talked about it. But ChatGPT doesn't know. And then let's test another paper. So that paper we published in 2013. In this work, we identified gene is actually kind of a special type of gene called long non-coding RNAs. It's called IOC90784. And here, it's too small. I will just read it for you. Expression of IOC90784. Well, I couldn't even see it. Have a protective effect on breast cancer patients. Okay, so we asked GPT 3.5. It said, I'm afraid I don't have any specific information about this. And then again, GPT-4. Well, this time I added please to be more polite, hoping it may work harder for me. And it seems it did, because if you look at, it actually gave a lot of information, although not very much related, but there's one piece of information. It says, IOC90784, also referred to as link 00907. Well, that seems it knows something about this, right? So, wow, I actually know something. So let me follow it up a little bit. So I asked, where did you find out that IOC90784 is also referred to as link 00907? And then he said, I apologize for any confusion. I was not really confused, because it's very clear, right? It says they're the same thing. No confusion. I just want to ask, tell me where you actually get it. And then I said, okay. But it actually says, these things can be found from a database called NCBI. Well, that's actually a well-known database. We use it a lot. So it's okay, let's search for it. And it turned out that these two things are actually different. They have different entries, different IDs. So they're not the same thing. And then I kind of want to push it a little bit further. Are they actually the same thing or not? I said, well, it actually completely walked back, and I must correct my early statement. And then a lot of other things not related. Okay, so it didn't work really well. Of course, you can test a lot. So in general, like large language model like ChatGPT, they have these four major drawbacks. So first, of course, training cutoff date, right? Because after cutoff date, it cannot. But the previous list was sometime maybe 2021 and then 2022, but the latest one is actually April 2023. But still, it's about half years, right? But then it will not update it soon. You will have to use it maybe for a few months, and then no any information after April 2023. But for scientists, what we care about latest research, right? Yeah, so certainly if you can only give me that information before that date, it's not very ideal. And then hallucinations. Then we all heard about it, and today we actually saw it, right? It's totally made up that. Who knows from where? And then a lot of times when you ask source information, it doesn't know. But in this case, it actually honest. It was actually honest. But sometimes when you ask, give me a citation, they give you. However, don't just cite it, because if you actually check, it's a fake citation. Yeah, so but that's just if you actually work with these large language models, you actually know, why they do this. And then in addition, if you ask more sophisticated questions and they give you answer, and you ask why, what's your kind of so-called chain of thought, yeah, it's also really hard to provide such kind of information. So how should we address these issues of large language models? And many scientists, including us, believe knowledge graph is the perfect solution. Of course, you may have a different solution, but I'm certainly happy to hear what you think about it. So what is knowledge graph? So knowledge graph basically is a structured way of representing our knowledge. So it kind of represents our knowledge in terms of a graph or network. So think about the knowledge, right? So at a very fundamental level, we have all the concepts, right? In biomedical science, for example, we have diseases, we have genes, proteins, chemical compound drugs. They are concepts, right? And above that are relationships, right? For example, this drug cures that disease, right? This gene cures that disease. They're all the relationships, right? Yeah. So those concepts and relationships form the backbone of our knowledge. Of course, there are other things, but they form the kind of really the backbone. Yeah. So we can represent such knowledge using a graph, and we call it knowledge graph. So how can we actually make or construct such a knowledge graph? And it usually takes 2 steps. So we construct knowledge graph from literature or raw text. The first step is we perform so-called name entity recognition, or NER, to recognize names or entities from text. For example, disease name, genes names, etc. Excuse me. And next step is to extract relations. Just like I said, right? Our knowledge has concepts and then relations among the concepts. Next step is to extract relations among these entities we recognize in the first step. And that gives us a knowledge graph. And you may be wondering, how well can we actually make the knowledge graph? And of course, that's also the question of these many other researchers and all of the funding agencies. So NIH actually organized a challenge called Litecoin NLP Challenge. And NIH actually, in collaboration with NASA, organized this challenge around November 2021 and February 2022. And this challenge aims for test methodologies for constructing knowledge graph, because they actually recognize knowledge graph is a very powerful tool, and people have been doing research on it, and then they want to see how well can you do, especially with large language models. They know the field has moved so fast, they want to see what the state of the art. So it has two parts. The first part is basically NER, recognizing the names, and second part, relation extraction, extracting relations. And for this, because NIH kind of promoting research in health and drug discovery, so this is a challenge covers PubMed literature, biomedical literature. It has so basically the organizers, they hire some experts. They read about 500 PubMed abstracts, and they recognize these entities: diseases, species, genes, mutations, chemical compounds, cell lines. And among these entities, they also labeled relationships, and there were around 8 relations among these entities. And we were given 400 abstracts to train our model, and then they kept that 100 abstract to test different teams' model. Yeah, so we participated in this challenge, and then fortunately we win the challenge. And there were many. You probably cannot see. Yeah, there were actually many teams from around nation and also from other countries. And with that, the pipeline and methodology we developed for the challenge, we actually did a large-scale information extraction of all the PubMed literature. We extracted information from more than 33 million. In fact, we actually did another update. We have now more than 35 million PubMed articles. We also integrated information from 40 different public databases. And then we also analyzed some public available genomic data sets. And once we analyze this data, we actually get the results, right? The results are also knowledge. We can put that knowledge into the knowledge graph as well. By the results, we have more than 11 million entities and more than 40 million relations, and we call it BioKG for biomedical knowledge graph. So this is the first time such kind of large-scale information extraction has ever been done, and certainly want to see what the performance of this large-scale extraction. If you have done some machine learning research, you know that many people publish papers, right, saying, well, we have developed this method, and then they work pretty well for that benchmark data, for that benchmark data. But if you actually use that on a large scale, and many times these methods don't perform really well, because a lot of times they somehow tune that so that it works really well on a benchmark. But in the real world, when you actually apply them into a very large scale, they don't really work well. So here we compared our model. So we randomly selected 50 abstracts, and then we used several people, including I actually read these abstracts as well. So kind of get a gold standard. We read them, we label them, and then we multiple people double check. And then with that gold standard, we compare our model performance with several human annotators. So here, our model performance, where pointer here? Okay, yeah. So we measure 2 performance metrics. One is FN score, the other one is accuracy. So our model has F1 score 0.77 and accuracy more than 95%. And for experienced PhD, it can reach about 0.65 or more than 0.65 and accuracy of 93%. And for graduate students, we actually hired biology graduate students from FSU. Their performance even worse. And then they all kind of worse than our model. Then we find out commercial annotation service. But there's a company from India. They always send me emails, ask, can we, do you need any annotation service or not? We say, okay. And then we send our data to them. And it turns out, they are actually worse than our experienced PhD annotator. So with this result, we actually were kind of surprised that our model now can beat individual annotators. So this had never been achieved personally, because at least I think in the last 2 or 3 years, and these deep learning models can actually achieve human level performance. We worked on this problem for more than 15 years, and so definitely a lot of breakthrough, a lot of work have really helped bring the field to this. There's something here, stage. Okay. Oh yeah, there's another interesting feature of the data set. I know the organizers also labeled the novelty of relations. So think about in a piece of paper, right? There are many relations. And then some relations are actually background knowledge. And some relations are novel because they say we've identified or we find A related with B, right? Or given some background knowledge. They labeled, well, this relation is actually novel, and some relations are not novel, meaning they are background. And our model can also make a very good prediction of this novelty. Here. Oh, it's not working. Let me see. Okay. Yeah, this summer we also participated in another challenge called Bio Creative Challenge. So this challenge has been around for quite some years, and this is the 8th round. So every round, every 2 years, they have one round, and then basically that's a challenge also can organize a community for masters in biomedical information extraction. And in this challenge, there were several different tasks, and one of the tasks called is end-to-end knowledge graph construction. And we also participated in that, and this time our team is called in Silicon, and we also ranked the first. So you can see actually, this time we have pretty large margin compared to some other competitors. So what can we do with the knowledge we extract? And actually, there are many different relations. If we look at individual relations, they are quite important for some different scientific disciplines. For example, mutation with disease. And that's important for genetic testing, if you know 23andMe, right? So this kind of relation is all they work about. Because they test your genomes and get some mutations and say, well, with this mutation, you have higher chance to get diabetes or some other disease. Maybe need to do a more frequent test than other people, or prepare for that. And for chemical disease relations, there are different type of relations. For negative correlation, basically means if you take this chemical or this drug, then the disease will be gone. Then that's therapeutic relations, and that kind of relation is important for drug discovery. Or you may take a drug and then, and that may cause some symptoms, and that's side effect, and that's important in the field called pharmacovigilance or drug safety. And there are some other important relations for different applications. So with this data, we can actually look at the trend of scientific discovery. As I mentioned, we can, in a paper, we can extract novel discoveries. So then we look at these novel discoveries. For example, we first just look at the entities. And then over the year, we see what the number of total entities for disease, gene, and chemical, and demutation. You can see that over the years, we start from 1900. And of course, in the early years, increasing very small, but then after 1980 or maybe around 2000, and all these, except diseases, because disease, really, we don't have a lot of new diseases, thankfully. But we discover many new genes and then chemical compounds and DNA mutations. And for relations, you can see also they increase quite fast. And here, one notable relation is the disease-gene relations. You can see that in the early days, there are not a lot, but then its proportion increased quickly. So that means, especially after 2000, so disease-gene relations means we actually understand disease much better, right, at molecular level. And this is, I believe, is partly by the kind of promotion of the NIH and NSF of translational science, because translational science, they say, well, you need to do something related to disease. You really need to understand disease. And yeah, so therefore we have a lot of disease-gene relation discovered over in the past 20 years. And then you can see that the chemical disease relations. Chemical disease relation basically means we're developing new drugs for disease, right? You can see that it kind of follows this also. In the past, maybe 5 or 10 years, increased pretty quickly. That means once we know more about disease at molecular level, that also help us to develop new drugs to cure diseases. Another thing we look at is we call it the rate of knowledge transfer, which is kind of the new concept, because previously people don't have this kind of data, so you can never look at it. So what we look at is, for example, there's one relation, say a gene to a gene relation, and discovered in a particular disease, say lung cancer. And then we want to see that for this kind of a relation, and in the next 5 years, how frequent people can identify such kind of relation. Basically, this kind of matters if somebody published something, right, in lung cancer, and then other people may read it. Those people may study breast cancer. When they say, well, this relation may actually be true in breast cancer, right? Let me study that. And then maybe then they do some experiment, they confirm, they publish in another domain, right, from lung cancer to breast cancer. Yeah, so we want to measure the rate of this kind of knowledge transfer over the years. And it turns out that actually the rate in the past, more than 20 years, actually gradually decreasing. So that means, well, there could be different reasons, but we speculate that because in the past 20 or 30 years, there's so many papers being published, right? And actually we felt, well, there are so many papers, we cannot even read them. We give up reading papers. If you give up reading papers, then you don't know the latest research, right? And then, of course, that may contribute to this kind of slow knowledge transfer, right? And how to address this? And then knowledge graph, right? Because now we have knowledge graph, we extract the information, we can automatically recommend all the new knowledge to people in different fields. And then they don't have to manually read all the papers. And I think that's a perfect solution. So next I will, how much time do I have?
Don't worry about it, keep going.
Okay, so next we look at the application of the knowledge graph, drug repurposing. So in the COVID-19 pandemic, we all know about drug repurposing, right? Because people are desperately seeking for effective treatment for COVID-19, and they try to find out the existing drug to cure COVID-19. There are so many papers on drug repurposing for COVID-19. So to address this question, what we do is we have relations between drug and genes. We extract many of that relation. We also have relations between gene or proteins with diseases. We also extract many of that relations. And then we also know how the drug affects gene and how the gene affects disease. For example, gene may be related to disease in a positive correlation fashion. And when this gene increasing, then we have disease. And then the drug with gene may be negative correlated. That means if you take the drug, the gene will be kind of repressed. Then with this kind of relationship, we can infer that the drug could be a treatment for disease, right? So we can actually make this kind of inference. And we actually design algorithm. It's not that straightforward when you actually work on very large scale, a lot of information. But we design algorithm to make this kind of inference, and then we apply that to COVID-19. So here, we did something nobody has actually did before. What we did is, well, let's assume we can do this at the very beginning of a COVID-19 pandemic. So we did that starting from 2020 and May of 2020. So we do this every month. So basically, at the very beginning of COVID-19, we don't know much about it, right? If you know nothing about it, you cannot do drug repurposing. But people start to do some research in public paper. For example, they identify some genes important for COVID-19. Once they identify some genes important for COVID-19, we can actually do drug repurposing because remember, right? So here, once we identify some genes, then we have this link. So this is COVID-19, this is some genes. But for these genes, people probably already published some papers about what kind of drug may be affected or affect these genes. And then we can make this link, right? So that's what we actually did. It's kind of interesting that you see, so yeah, this is a little bit of basic picture, so you need to kind of process this a little bit. And in March 2020, and this bar is number of genes, and then this axis measure genes, so maybe I think 3 or 4 genes. So basically, it's very early, right? People only publish a few papers and then they identify a very small number of genes related to COVID-19. But with only 4 genes, we can actually repurpose many drugs. So this is repurposed drug. And then this bar is validated. So we repurpose more than 600. So that means, yeah, probably these 4 genes kind of well-studied genes. People already knows a lot of drugs actually can act on these genes. But it means later on, because we actually scanned all the PubMed literature, so we actually know later on what drugs have been used to treat COVID-19. Or we look at 2 sources. One is the PubMed literature. People report that we actually use a drug to treat COVID-19. Or in a clinical trial, people try that drug. Of course, clinical trial doesn't mean that drug will actually be effective. But being able to put on clinical trial, that means it's certainly a good hypothesis, right? So here I want to emphasize that knowledge graph give you hypothesis, right? That's it. But give you very good hypothesis because we make inference. But that means the relation is actually a good one. You have to test it, right? Yeah, so as long as it's good hypothesis, then I think we did a good job. So no matter it's reported by PubMed or drugs on clinical trial, that means they are good hypothesis. So you can see that around 1/3 of those we repurposed actually were validated later. Of course, those non-validated, that means they're not good, right? Maybe they're still good, just people haven't looked at, haven't seen that. So this percentage is actually, I think it's very impressive because we read a lot of literature before, and it's really, in fact, nobody can actually calculate this. Because think about, if you repurpose, let's say, 600 drugs, right? But how do you know how many were actually validated? To know that, you have to scan all the literature, right? And nobody can ever do this. Yeah, because you can, to search each one, it takes a lot of time. And then if you select a drug, you search, you have to read it, right? You have to know whether you have reading, it's basically an impossible task to manually to search these 600 drugs and then read all the literature. Yeah, you have to use automated approach like ours. And then, so basically we have kind of all the knowledge in a structured form. Only with all the knowledge in structured form, you can do this kind of evaluations. So we did another study of drug repurposing for COVID-19. So this time we assume we know all the knowledge. Basically, we didn't do that kind of real time, do it month by month. We just did at kind of today, assuming we know everything. And so you can see here, this bar means how many genes connecting the drug with the disease. And it's really surprising to me that all these candidates identified, there are many genes connecting the drug and disease, not just one gene. So remember here, this is our hypothesis, right? So before we do this drug repurposing, I actually don't know how much knowledge we have in the literature. I have no idea because nobody has done this. And we may not be able to find any. I don't know, yeah. And it turns out there's so much information. And then nobody actually knows it. We kind of very surprising to us. For these drugs we repurpose COVID-19, they actually act on, you see, on average, maybe 30 genes. And all these 30 genes are actually related to COVID-19. So that means evidence is overwhelming, right? We actually checked many of these, and we find out, wow, all these genes that people reported related to COVID-19, and the drugs actually affect so many genes. And then after reading the literature, you think, well, they should try that drug. You really should try it. And it turns out, okay, so all these are our top hypotheses, right? And then these red ones reported as treatment. Basically, majority of our hypotheses, they are indeed reported as treatment. So that means they are actually good, good hypotheses. And then the green ones, they're not reported as treatment, but hypothesized. Because in COVID-19 era, people read a lot of hypothesis articles. Because even hypothesis works well. And then they say, well, we believe this drug is really can be used for COVID-19. You guys should try it. They just read the paper and get published. And then you can see that these green ones are hypothesized. As I mentioned, even hypothesis are good discovery, right? And people publish hypothesis article. Only one not reported as treatment or hypothesized. But this rate, I think, is still very, very impressive, I believe. Yeah. So next, we look at drug target identification. So in drug discovery, you know that these pharmaceutical companies, they spend billions of dollars, and the success rate is really low. And this drug target identification is the first step, very important, because once identified target, you can design drug for it, right? So here our strategy is, well, there are genes that have been reported as drug target, right? So that's a direct relation we extract from literature. We also extract other genes that actually regulate these genes that are known as drug target. Then what about those genes with this disease? Can they be drug target as well, right? So very simple hypothesis. And then we have those individual relations, right? We can make a simple inference. And then we say, well, let's see how this strategy works, right? Okay, so again, yeah, this figure you need to kind of spend some time to look at it to really understand. Well, we did our drug target identification again yearly, starting from, I believe, 1988. So basically, we go back to 30 years ago, and then say, well, at 1988, we don't know all the literature after that. Given the knowledge we have at 1988, well, so we did this for lung cancer. So let's predict drug target for lung cancer, just using this simple idea. Because at that time, people already know some genes are drug target for lung cancer. And then at that time, people also know some other genes regulate these genes. Then we say, well, let's predict those genes are drug target for lung cancer. And then you can see that, so this bar is our predictions, so that's the numbers. And you can see that in the early days, because we don't have a lot of knowledge about genes, about lung cancer, of course, we cannot make a lot of predictions. But you can see that as time goes, we actually can make a lot of predictions. And these dark ones are validated. Validated means later on, people actually reported those genes, they are drug target lung cancer, okay? And this blue line is how many years on average it took for the people to kind of report those. So you can see that on average about 15 years. So that means we predicted something. On average, after 15 years, people report, oh, that's drug target. Okay. So then we look at another kind of dimension for each year. And then if we look at all the drug type people reported, okay, and then what the percentage of these reported drug targets were predicted before by our algorithm. And it turned out on average about 40%. So that means 40% of the drug target people report have been predicted on average 15 years ago. Well, that's think about, almost half of these new discoveries we predicted 15 years ago. And it usually doesn't take so much time to validate a drug type. I think 5 years probably enough. That means if we actually can kind of go back time and predict these drug targets, and then once we predict it, we tell the researchers, okay, that's a potential drug target. They start their experimental validation. They may take 5 years to validate that. That means they can publish their results in 5 years, not 15 years, right? That means by doing this, we can significantly accelerate scientific discovery. But think about it, it has its power, right? Because now you can extract all the knowledge in structured format. You can actually do all the calculations, you can recommend to people. And then, of course, people can read the evidence we provide. If they think, well, it's actually interesting, they can do it. And this, in principle, can certainly help people accelerate their scientific discoveries. So now we go back to the major drawbacks we mentioned about large language models, right? So for training, cutoff date. So for our knowledge graph, we actually do daily updates because PubMed publish papers every day. Once they publish, we grab the paper, we process it, we update our knowledge graph. We can do daily update. So for large language model, you cannot do that, right? Because training ChatGPT 4 or whatever is a huge task. We all know that. They use a huge number of GPUs. But with knowledge graph, we can do it pretty much real time. And hallucination, we don't have that. We extract exact information. We know that A regular B, B regular C, whatever, right? We extract that. And then our extraction, as we see, at human level, is actually depends on what kind of expert you use. If you use somebody who's not that good, we actually beat them, right? And then we, of course, provide source of information because we extract from each paper, and then we build the interface, and then you can actually see the knowledge graph. You can click edge, and then the paper actually pop up. You can read the exact sentence we extract. So everything you can trace back where we get it. And the reasons here you can see we actually perform some simple inference, right, from A to B to C. This, I think, in principle, can help large language models to make better reasoning. Okay, so with our knowledge graph constructed, we build this interface, and you can search the knowledge graph, and by providing entity name, the first entity name, and then the second entity name, and then you can also use some other conditions. And so from a traditional standards, this is good because it provide the people with we think it's kind of versatile way to query knowledge graph. But so by the way, I actually took a year of I took a leave of absence and then started my startup. Then we developed this in my company. And so once we developed this, then we started to talk to the potential customers. Then we realized it actually not as good as or as powerful as we thought, because these biologists in pharmaceutical company, they have all kinds of questions. So this interface is a kind of a traditional way to allow people to search a database, right? But it cannot address so many different questions these biologists have. However, we do have data. So for all their questions, we can write some additional code to solve them. But you cannot scale up that, right? So then we realized, it wasn't that great. But then how should we solve that? So that's a solution. So now we can actually think about large language models, right? So we can really use the power of large language model with knowledge graph. Because, so right now what we have is, you can access this knowledge graph with a very rigid interface, right? I just showed you. But that interface can only allow people to answer some questions. But they can't have any questions. But whatever that question they have, they can express using natural language, right? So by combining large language model with knowledge graph, we allow people to ask questions using natural language. And now we have some open source packages, LangChain and some others, that actually do this job. And this is the work we are working on. In fact, I was thinking to talk something about that. That's why I gave that title. But we are still working on that. I don't want to talk about some premature results. Hopefully, maybe next time, if you have this, I'll come back and show you our latest result. And so we can actually allow people to ask natural language that will be kind of parsed through large language model. And large language model will actually from natural language to generate queries for the graph, right? Because graph database, right? They can generate queries. And then the query, we use that query to query data from knowledge graph. And then that data will be put back to large language model. And then this LM will actually provide you the answers with, again, natural language. Yeah, so basically, that solves the problem with our limited interface. So our goal is to develop a general purpose question answering system for biomedical science. We hope by combining large language model and knowledge graph, we'll be able to provide something really powerful. Because think about the example I gave you. ChatGPT really cannot help me in my research because for all these limitations. But with knowledge graph, it really fills in all these issues large language model has. But with knowledge graph alone, we have other issues too. But then that can be solved by large language models, right? So together, it's really perfect fit. And now, if you are kind of keen to all these latest developments, people talk a lot about AI for science. Yeah, I believe this is also the way to go because AI will definitely help scientific discovery in many ways we know or we don't even imagine. And but how do we actually move forward? A lot of people discuss all different solutions. I believe this is one of these promising solutions. Yeah. But think about it, right? You have to have this knowledge in this kind of structured format to really help AI and training deep learning models. Okay, do I still have time or no?
I think now we want to have some time for questions.
Okay, yeah, actually I'm finished. Yeah, I have 2 questions, but you can ask or yeah, we can discuss. All right, yeah, thank you.
Thank you so much. That was really amazing. Does anyone have any questions?
Yes.
Could you see a similar system working in other fields that may have like, because I'm thinking of like sociology and economics, where they'll use similar methods of like statistics and correlation and understanding relations, but it involves a lot more like language. They write a lot more, it's a lot more descriptive, I guess, and qualitative. Would something like this system be adaptable to that, or does that kind of introduce its own challenges?
Yeah, good question. So, well, I believe knowledge graph can handle all knowledge, and that's our kind of future goal, to not just build a tool for biomedical science. Instead, we want people to put all knowledge in knowledge graph and to power all different science. I believe, yeah, that's definitely possible. Of course, for other disciplines, for example, here we use NIH Litecoin and LB challenge data sets, right? Yeah, in some other discipline, you probably have to generate your own label data. Yeah, although using LM, you can do, say, 0 shots, few shots, but from our experience, yeah, performance is far from using a decent label data to fine-tune large language models. Yeah, but yeah, I think the answer is definitely you can do it. Yeah. Well, if you don't questions, I actually have yeah, 2 questions at the end of my talk. So we all kind of wonder, right? Where are we, in terms of artificial general intelligence? And everybody has their own take. And my opinion is, well, I don't think we are anywhere close. Of course, there's a lot of hype. Say, oh, Google developed something kind of have conscious, and then and OpenAI developed something close to. But I don't think so, because I used a lot. If you use it, it's powerful, no doubt. It can do. I believe. I definitely believe it, and then that's why we are working on that. But general human intelligence, I don't think we are anywhere close. Yeah, so that's my opinion. But it can do a lot, and it can definitely, in many tasks, a lot of tasks, we think it need general human intelligence, it may not actually. For example, like Go, right? Weiqi, right? So I actually started studying deep learning from AlphaGo, because I played Go many years ago, and then I still like to play it. I thought that game really requires fuzzy kind of thinking, computer kind of feelings, right? You don't think. You look at it, you play with a feeling because you cannot calculate all that. I think I thought an AI cannot handle that. But it turned out, yeah, they solve it, and then it beat professional players, and then it actually invented plays we have never thought about in the past 2,000 years, and then professional players now learn from AI. But now if you kind of look at it, it's just very sophisticated pattern matching. Yeah, it doesn't, well, maybe we think we have to solve it with a lot of our human general intelligence, but computer actually solve it from some other ways. It doesn't have to involve so-called general, human intelligence. Well, next, what should you do? Yeah, I was thinking we have more general audience, and I kind of tell you guys, well, you need to really embrace AI. But now I think many of you probably already in it, right? Because I saw we'll have some interesting talks by the students. But still, I think, so in terms of AI, there are several hypes, right? We all know that. And then kind of hype and die. But this time, I think it's finally there. And we all have to embrace it. Yeah, either you really learn it, if you're good at coding, math, and be very good at it, yeah, because AI time, definitely comes already. And if you're not much into math, statistics, or programming, but use it. So at least at abstract level, you have to know what AI can do or cannot do. So you can at least know what input, what output. Treat AI as a black box, right? But still use it. Yeah. So when I teach my students, I sometimes tell them, oh, if you have questions, sometimes you cannot always find a tutor or you can ask a teacher, but just Google. And some students, oh, you're a teacher, why ask me to Google? But Googling is a skill, because I actually learned in my experience. Sometimes if you are new to it, there are always answers. And then once you actually learn more and more how you can search, and you become better, and you can always find a solution. But of course, Google is hard. But now, we have ChatGPT. Yeah, it's much better. However, you have to learn to use it. So there's something AI can certainly do. Everyone knows you can easily ask, it tells you, no problem, right? And there's something AI cannot do, no matter who uses it. But there are a lot in between. That is something you have to learn. So yeah, first, sometimes you don't know AI can actually do. And then if you don't know, you say, it won't do. You won't even ask, right? But sometimes you know it can do, but it's not that simple. You have to kind of guide it. Not through one step, it's through several steps. Yeah, but this, you have to learn. And then this will actually, even you don't develop an AI algorithm, right? But being able to use AI very effectively will actually differentiate you with many other people. Yeah, okay. All right, thank you.
All right, thank you very much. All right, so now we have a little bit of a break until about 3 or so. So feel free to grab some food, some snacks over here on this side. Feel free to chat with each other, and we'll be back in a few minutes. The student presentations will be in sort of a flash talk or lightning talk style format, where each students will have 5 minutes to present. For the students, just so you kind of keep track of time, I'll be sitting right there and I'll have little 2-minute, 1-minute warnings. And then also for everyone else, please save all of your questions for after all of the students have finished presenting. We've allocated a good bit of time for Q&A and discussion after all of the presentations. All right, and so our first student presenting is Josh Briley, who will be presenting using machine learning to predict fire spread. Then you advance it forward with this,
Okay.
even though this is
Cool. All right. Hi, everyone. Good afternoon. My name's Josh Briley. Today I'm going to be talking about the research I did last year in Europe. And that was using machine learning to predict fire spread and fire dynamics. So before we get into anything too much, I just wanted to talk a little bit about the methods of the overall project. So as we move forward, you kind of had some background knowledge. So this fire dynamic to the right here you can see, so you just have the meters and then the spread over time. So you can see that the black part is where the fire started from, and then as time progressed, it just kind of spread out. And to predict this model, I used a MATLAB code as kind of a basis. And a professor in my department already developed the MATLAB code, and it had already been proven to be accurate. So we used that as our training and test model for the machine learning code. To be able to run the MATLAB files, I submitted a job to the SSH, or using an SSH, I submitted a job to the RCC. And then the percentages that I decided to use for the machine learning model was 85 for training the model and 15 to test the model after it had already been trained. And then to kind of give you a little bit of an idea of what the machine or the MATLAB model or the physics-based model looked like. You can see here it kind of spreading. And then on this bottom little table is the parameters that were set for this specific model. And then since we're kind of on a time crunch, I think you kind of get the idea. And then here's just a different origin starting point. So it's kind of like a V shape, where the other one was like a straight line. And then the wind speed and sync terms and stuff is a little bit different as well. And then to the left is just the initial starting spot. Okay, so I just kind of gave like a little bit of preview of it, but the input parameters for this is going to be the background wind speed, the sink strength, which is basically just how much of the heat is being absorbed into the environment, the vorticity, and then the flame out time, ignition probability, and ignition pattern field. So that's just basically the odds that the fire will move to the pixel that it's next to, and then the starting location. And then the output is that first arrival time map that I was talking about previously. So there's just kind of like an easier way of looking at it. You have the map to the right and then all the inputs. So this gives you an idea, like a more like quantitative approach to the inputs. So in the parentheses is like the different options that we had for the model. So just for example, with the wind speed, it was either 2 meters per second or 8 meters per second. And then the flame out time, so how long the flame would last after it already started burning, was 9, 12, 15, etc. And then once again, I don't know if I commented on the specific samples, but it was 4,250 and 750 to make the percentages. And then for the ignition, the starting location, we had it all as like a straight line, and then just the angle from that line is how we had the starting location for the fire. We don't have like a whole bunch of time to go into like the in-depth model and stuff, but like if you're really into like the super technical side of the model, this will kind of give you an idea of that. But basically there's a 160 by 160 by 6 image. So the 6 is for the 6 different parameters that I mentioned before, and then the 160 by 160 is just the map that it's starting on. So even though it's on at 200, it's actually really only going to like here. Yeah, and then the output is a 160 by 160 by 1, which is just like, basically the 2-dimensional image. And then now kind of getting into like how effective the model was and stuff like that, we can look at the mean squared error over the number of epochs. So as you can see, the model was, pretty accurate and stuff. We got that nice little curve we want, and then the number of epochs was obviously a good number. And while this is good and stuff, I always think like a visual example is a little bit more, because these are all just kind of like arbitrary numbers. So if we look at to the left here, we have the numerical prediction on the physics model, and then to the right is the machine learning output. So you can see it's obviously pretty similar. And then here's just like a different starting location to try to prove that it wasn't like, it's not just that one example that happened to work out that way. Like they all are pretty accurate. So at this point, you might be wondering, okay, well, you have this physics-based model that can run on MATLAB that can predict a fire grate. So what's the point of using like machine learning or convolutional neural network to predict? Because you can just use the physics model for everything. And the biggest reason for that is just the time. So while it might take a second to train the machine learning model, so that took about 910 seconds. And all these times are kind of approximate because as it goes from from different time to time, it's going to vary. But it was like roughly 910 seconds, depending on like the batch size and stuff like that. But after the model was trained, the time difference was very significant. For the convolutional neural network, it could do 1,500 samples in less than a second, while the physics-based model took like 196 minutes to do 100. So you could see if you're trying to predict how fire will spread in like a wildfire, or you need to make an evacuation procedure or anything like that, that just might not be enough time for something like this, where the machine learning model could quickly inform decisions. Yeah, that's all I have. Thank you so much for listening to me. I'd be remiss if I didn't mention my research mentor who helped me with this project. She's now at the University of Kansas, but Dr. Shin Tong helped me a lot with this. And yeah, go Knowles.
All right, our second student presenting is Tushar Chandra Mondol, who will be presenting reinforcement learning-based routing for interconnection networks.
Thank you. Hi everyone. So I'm a PhD student in computer science, and I'm working with Dr. Shiniwan to for this project. Actually, this is a reinforcement learning-based routing for interconnection network. So you can see my content overview here, and like the first question can come to our mind, like, okay, what is interconnection network? So if you want to do high performance computing, so you need to use so many computers together, right? So you need to connect all the computers, processors, or memory modules together. So interconnection network is nothing but the network by which you will connect all those things. So now the next question is, okay, what I'm trying to do here in interconnection network. So it's like adaptive routing. What is adaptive routing? Like if you have a source and destination, you can have a multiple minimal or non-minimal path. So, but using the minimal path is not always the wise decision. Why? Just let me give you an example. Like, suppose this is the source and this is the destination. Like, so there are 3 flows going from source to destination, and this is the mean path. Okay. But so if you just send all the 3 paths like over this mean path, like these links are shared for 3 flows actually. That means there will be a flow flow collision or like link congestions. But if you do what, like if you just take like, okay, if you send one flow to the mean path and like 2 other flows to 2 other non-minimal path, although non-minimal path, the latency will be higher, like the time will be higher, but like in total, like there will be no flow collision. So that's why in total, the system's throughput or like system performance will be a lot better. So then another thing, okay, what is reinforcement learning? So it's the branch of machine learning. Like, okay, so here actually our agent interacts with the environment and like do some take some actions, and like it gets some reward back from the environment, and like by this feedback it always improves itself. So actually the goal is to maximize the total cumulative reward, and by having the best policy. So there are many value functions like that. Like one of the most popular one is the Q value function, or like the quality value function. So, and now let's see what are the challenges of adaptive routing. Like what are the challenges? So if you see like, okay, there are multiple, like there are two paths here, like this is the source and suppose there is the destination, so two paths. So a router has only the local information, like this is a router, only it has the local information. What is the local information? That means it only knows, okay, how many packets are waiting to use this path, or like to use this link, and how many packets is waiting to use this link. You can see like a little number of packets is waiting to use this link, but if you just consider the whole information, like global whole path, so many packets are waiting to use this path. So based on these information, so okay, so if we just take, okay, so only one packet is waiting to use this link, so let's try to send the next packet using this link. So it will be a bad idea, because like like later it will have a less like congestions. So that's why we need to estimate this global information for which will be available to each router. So here reinforcement learning can help us to estimate this global information. So why have you chosen reinforcement learning over other machine learning techniques? Like, again, like network states actually changes over the time, because the traffic pattern, or like the traffic pattern means like different types of application wants to do different things. So, and this changes over the time. So like pre-given data set or experience from anybody else is not or like supervised learning is not a very good idea for this kind of scenario. And again, you need some human effort, but like as it keep changing the network state, so it's actually not a good idea. So, and reinforcement learning, obviously it learns by itself, and like it has a continuous learning feature. So that's why we have chosen reinforcement learning here. So how can we relate reinforcement learning things into our adaptive routing in interconnection network? Like we can think of like our topology as the environment, all the routers as an individual agent. So it will be a multi-agent reinforcement learning based system, okay, model system. And the states is like the different traffic conditions, and the observations, and actions is like just choosing the next router, or like from here, okay, I'll towards the destination, I'll send my packet to the next router. So that's the actions, and the reverse is like the traveling time between these two routers. So what are the challenges we have to face, like if we want to design a model-based routing system in interconnect? Actually, here we need to have several path diversity. That means obviously as many paths we will have, we can distribute our packets to that over those paths. So it will be great. But like we have also the restriction on hop count, because like you can't just like route your packets without even progressing to the like destination. So there is a restriction on the hop count to avoid the live lock and deadlock on your system, and the restriction on link uses. So in interconnection network, there are like several kind of links. Like we can call it like on local links or global links. So global links tends to have like higher latency than the local links. So because it's wide, well, like it's lengthier than the local links actually. So we need to restrict our routing algorithm to use like. We need to use it because like these are actually truly like distributing your packets over different groups, but like yeah, there should be some kind of restriction. And then again sparse update of qtable and qtable updating mechanism, which is like generic to any kind of routing scheme. That means like your qtable update mechanism can adapt to any routing changes also, and the qtable convergence. That's it. So here we are working on routing called qadaptive, so which is q-learning based adaptive routing. So there are actually three principal components, like maintaining a qtable for each router, and like the routing with qtable and updating the qtable. So here you can see this is the qtable. Like each router actually maintains this and learns this qtable. So here we have grouped several routers into a group and like merge them in a single row, so that like we can mitigate the sparsity like of update. So and here actually we do have multiple ports. Multiple ports means like multiple links connected or available to that router. So here we will store the Q values. Q values is nothing but the estimated latency. That means estimated time. Like suppose here this means like, okay, if you send your packet through this port 1, so it may take this much time to reach to the group 1. Like to the destination group, and after getting to the destination group, it's like you can just minimally forward the packet. It doesn't mean, because like in destination group all the routers are connected each other, so there is all-to-all connection there. So now how the routing with the qtable, how qtable works, like so when a router receives a packet, it knows, okay, what is the mean path port, like what is the mean path, because by looking at the tuples you obviously know that. So it will get the estimated mean path port value, which is we are calling it q mean, from the q table, and again it will get another best path port. What is best path port? That has the lowest q value, right? Now that we are calling it q best. Now we have got two things, q mean and q best. Now we'll compute the difference between them. Like now if that difference there will be a predefined threshold just to bias towards the mean path, because like obviously taking mean path there is a little bit bias, so that's why we are using a threshold value. So if that difference is less than the threshold, then we'll send the packet through the mean path, and if it is greater the threshold, we'll send the packet to the non-mean path. So and again, so this is actually we're saying it, okay, temporary outbound port, but the final outbound port, like we have like to tackle the exploration trade-off, like we have used a simple but yet I think it's effective like epsilon greedy policy. So to get the final outbound port, that means epsilon, like with epsilon amounts of time you will randomly choose a port, and most of the time you will choose this temporary port, like already exploited port. So now here, how the updating Q table works. Suppose here S is the source and D is the destination. So you want to send the packet from source to destination, and in the path there is a two router X and Y. So router X has already a value, estimated value of QX. So QXYD. That means like, okay, what is the estimated value, estimated time to send a packet from X to router D through router Y, neighboring router Y. So it has already this value. So when router X sends a packet to router Y, and after receiving the packet, router Y does what? Router Y again gets the lowest value, okay, how much time it needs to send to router D, and then it propagates back this value to router X. So you see, like router Y is more close to the destination, so obviously it will be more accurate to this information will be more accurate. So it will propagate back, and using that information, router X will update its own value QX. So it will be, as it is more accurate. So I think it will learn, like it will be also more accurate after a while. So here you can see this is the equation, and like I have. This is the immediate reward. Immediate reward is just like the traveling time from X to router Y, and we have used actually two learning parameters like alpha and beta, because like there is a research work called hysteretic Q learning. They have showed like, okay, if you just always increase your Q values but not decrease, like suppose you are avoiding a penalty, that you can stuck into a suboptimal solution. So that's why, like suppose you have taken the best decision, but any other router, like team member, we are calling it team member because like any other router in the path have actually made a bad decision. So for that bad decision, you cannot be actually penalized. So that's why like they have suggested also using the two learning parameters. One is for like increasing your Q values, and one is for decreasing your Q values. So by this way, actually we've update the Q value, and the routing works like this. And like, yeah, but I haven't gone through the it is basic level, but because like there are some other restriction obviously also as there are several groups, but like I'm not going through that. And so again, like I'll now come to the conclusion, like due to his learning by own policy, it's obviously a very good choice. And like I have gone through several other reinforcement learning based techniques for different high performance to solve different high performance computing based problems, and they have done a great job. Actually they have done some very good improvements. So that's why I thought, okay, why not in applying that thing in like routing also. So yeah, so if anybody is interested, you can also research and like do some good research on it, and you can take it forward. Yeah, thank you. Any question?
Right, thank you. All right, so our next presentation is Madalena Bulat, who will be presenting deepfake information manipulation. Can you recognize it?
Hi, my name is Madalena Bulat, and I'm an undergraduate student majoring in computer science. I started participating in research my sophomore year, and I'm extremely grateful to be able to continue conducting it. One of my research projects involves how individuals detect deepfakes using artificial intelligence. This presentation is based on a research study conducted in previous semesters, as well as a paper that was written and submitted for the 2024 iConference meeting. Deepfakes can refer to information, a fact, an object, or a digital artifact that has been manipulated convincingly using technology. Deepfakes are a specific manipulation technique where people digitally alter, modify, or replace images or videos with the intention to change people's perception of reality. For this research project, we tackled the question of how whether or not users can detect computer-manipulated images through a series of surveys and questionnaires, and also whether these users trusted the images that they saw. We looked at something called the interpersonal deception theory, which is a communication theory that attempts to understand how individuals handle real and sometimes perceived deception at the interpersonal level. The theory breaks down the deceptive process and explains tactics employed, such as falsification, where information is forged or invented, concealment, where truthful elements are taken out, and equivocation, where vague information is used to mislead. The result of these altered images could be that they make us question whether or not what we see and hear is real. This doubt can affect public discussions and the trustworthiness of evidence that are presented in media. Software that detects deepfake images typically works by analyzing the content of an image or video to look for inconsistencies that are not usually present in natural images. Deepfake technology uses artificial intelligence and machine learning algorithms, particularly generative adversarial networks, to create realistic-looking images and videos by superimposing existing images and videos onto source content. To combat these advanced manipulations, deepfake detection software utilizes a few different methods, such as machine learning models, which are trained on datasets containing both real and deepfake images. The model learns to differentiate between the two by recognizing patterns and features that are indicative of deepfakes. Another one would be analysis of physical inconsistencies. Deepfakes often contain physical inconsistencies that can be a giveaway. For example, the blinking of eyes in videos might be unnatural, or the lighting and shadows may not correspond to the environment. And lastly, biometric analysis. This involves looking at the finer details of human biology, such as the way the skin pores and heartbeat and blood flow affect the appearance of a face. Deepfakes often fail to replace these subtle details accurately. In an effort to understand and counteract this, our research team has been working with an innovative piece of software known as Veracity AI. It's currently under development at the School of Information with the generous support of Dr. Shoyan Metcalf. The essence of Veracity AI lies in its ability to detect manipulated images. Specifically, Veracity AI is a prototype for deepfake imagery analysis using deep learning models trained to detect splicing, inpainting, and copy move manipulations. These techniques are the backbone of what we now commonly refer to as deepfake technology. Splicing involves taking portions of one image and grafting them onto another, creating a new composite image that appears to be a single, unaltered photograph. Inpainting is a digital restoration process. It is a way to fill in missing or unwanted parts of an image. It can be used to remove elements from a picture, such as wires, signs, or even people, and fill in the background as if they were never there. With deep learning algorithms, inpainting is now capable of generating pixels that match the surrounding area. Lastly, copy move manipulation is a technique where parts of an image are copied and pasted within the same image, often used to cover up elements or to clone objects. This method can be exploited to create more of something that was less of, such as crowds, or to fabricate scenes by duplicating elements within that scene. The early stages of Veracity AI used something called the ensemble method, where it showed the manipulated parts of the image through color coordination. The parts of the image that were manipulated were in black, while the parts that were authentic were in white. Gray corresponded to undetermined. As you can see in the image above, the ensemble method was used to show what parts of the image were manipulated. Sorry. It's not working. The button. Maybe here. you. And lastly, it's just the conclusion. Going forward, we want to improve Veracity AI so that it can not only check if images are real, but also work on sound and video. And this will make it better at spotting and dealing with deepfakes in a more complete way. Thank you.
All right, thank you. All right, so our next presenter is Sahil Chugani, who will be presenting Optimizing Fantasy Football Drafts.
Hi, I'm Sahil Chiani, and today I'm going to be talking about how to optimize fantasy football draft strategy in the first 7 rounds. If you don't know about fantasy football is a hobby where with random people or with your own friends, you make a fantasy football league. And these leagues are made out of teams. These teams are made out of random NFL players. These NFL players, if they do well in a certain week, they will gain a lot of points. And if they don't do very well, they won't gain that many points. These player point totals are added up for each team, and the team with the higher amount of projected points will win every single week. Now, for fantasy football drafts, people draft their fantasy football teams typically in June, July, or August. This is how teams are created, and I want to optimize this so that we have a strategy to help us win as much as possible. First, I'll dive into some assumptions. Our first assumption is that the more projected points a player has, assuming that the position is the same, we would rather have that player. Let's say player A is a wide receiver, and they're projected to have 240 fantasy points. Player B is a wide receiver as well, and is projected to have 230 fantasy points. Regardless of what the so-called experts or eye tests say, we will always want to choose player A over player B. Our next assumption is drafting the top 7 starters is optimal. In fantasy football, our players each are assigned to positions, such as quarterback, running back, and wide receiver. Our assumption states that we want to draft the 7 positions that will score the most points. This is our quarterback, 2 running backs, 2 wide receivers, 1 tight end, and a flex. A flex can be a running back, wide receiver, or tight end. We decide to omit backup quarterbacks, backup tight ends, defenses, and kickers because they won't be on our starting lineup every single week, and they will score less points than these top 7 starters. Our final assumption is that it's not optimal to have a second tight end in the flex spot. This is because tight ends in general score fewer points across the board than running backs and wide receivers. Therefore, we'd rather have a second running back or second wide receiver than a second tight end. Going into our methodology, as I stated, we want to maximize the amount of projected points that we have in our first 7 picks. To do this, for each pick, we can choose between at most 4 positions: quarterback, running back, wide receiver, and tight end. If we go through each possible combination in order of the picks in our first 7 rounds, there are 840 possible combinations and orders. In my study, I simulated each possible combination, and after simulating them, I decided what the trends were in terms of which position should be drafted first and which players were most commonly drafted. In terms of my coding, there are 12 pick slots. So for 12 teams, 1 team is picking first, second, third, all the way through 12th. For each pick slot, I simulated 840 combinations for each possible combination in order of the positions we can draft. Assume that one user is drafting according to one of these combinations, and everyone else is picking according to ADP, or average draft position. This is basically where everyone else is drafting most commonly at that position. We simulate each combination for 840 combinations for 12 picks and find out which positions and which picks will result in the highest points. After that, I applied these strategies to mock drafts in ESPN because it's one thing to simulate it with average draft position, it's another thing to do it in real drafts. So I did it in mock drafts, which are pseudo or fake drafts, which don't really result to anything, but they give us an idea of where people are actually drafting. After each mock draft, I would calculate the projected points of my 7 starters relative to everyone else. If my 7 starters had the most projected points, then I had won the draft. Otherwise, I would have lost the draft. I did this about 50 times and reevaluated my strategy based on if I won or lost drafts, and I applied these to 5 real fantasy football leagues. In 4 out of the 5 leagues, applying my strategies from my simulations, I was projected to win in 4 out of 5. And currently, my teams are all doing really well, and I'm projected to make the playoffs in most of them. Overall, I would consider this project a huge success. Thank you.
All right. Our next student is Reagan Bourne, who will be presenting Artificial Intelligence-Powered Smart Cities.
Sorry, it's like all falling. Hi again. So today I'm going to be sharing my current research project, which is Artificial Intelligence-Powered Smart Cities. So currently we are focusing specifically on electric vehicle adoption because it represents a crucial element in the transition towards sustainable urban living, and artificial intelligence can also play a key role in addressing some of the challenges faced with electric vehicle adoption. This research is through a directed individual study with Professor Guang Wang in the Department of Computer Science, and currently we are still in the beginning stages of this research project, so today I will just be sharing the findings of my literature review, our survey design, and our future goals for this project. Uh-oh. Do you want me to click it? I don't know what's wrong with it.
If it happens again, just hit that little one right there.
Okay.
And then, boom. There you go.
Thank you so much. So I conducted a literature review about the drivers and barriers for electric vehicle adoption in rural and urban communities. And today I'll be sharing some of the key details about adoption in rural communities, as I think it is more significant since they encounter a greater number of barriers for electric vehicle adoption. So the main drivers for electric vehicle adoption in rural communities are government, financial incentives, savings on fuel maintenance, and new economic development. The main barriers for electric vehicle adoption in rural communities are range anxiety, high costs, and installing and maintaining charging stations. The United States and several other countries around the world offer many financial incentives for purchasing electric vehicles, some of which are rebates and tax deductions such as electricity discounts. In addition, some countries are not only offering tax relief, but are also offering free toll exemption, free parking, and free charging stations, which is a huge driver for adoption. Also, while electric vehicles typically have a high upfront cost, they are proven to have a lower total cost of ownership when compared to conventional vehicles, which is due to lower fuel maintenance costs, which is another very important driver. However, range anxiety is the biggest barrier for electric vehicle adoption in rural communities. It is essentially anxiety surrounding how far electric vehicles can travel without running out of battery. This is especially significant because there are very few charging infrastructure in rural communities, and since rural areas are more reliant on personal vehicles due to the lack of public transportation. The unavailability of adequate charging infrastructure is one of the biggest constraints for electric vehicle adoption in rural areas. Rural areas are also characterized by lower household income, which by definition means that they also have less disposable income. This makes rural households very sensitive to the high upfront costs that are often associated with purchasing electric vehicles. So our next step in our research project is conducting a survey questionnaire in which we are using a conjoint experiment. We chose to use a conjoint experiment since it allows us to understand the trade-offs that consumers are willing to make when considering purchasing electric vehicles. The introduction for our survey is as follows. The range of travel for a new typical electric vehicle is 250 to 300 miles before it needs to be recharged, and the cost of an electric vehicle is usually $10,000 to $12,000 more when compared to a gasoline vehicle. Both foreign and domestic automobile manufacturers sell electric vehicles, which now account for about 15% of new car sales in the United States. Charging an electric vehicle is about 3 times cheaper per mile than fueling a gas-powered vehicle. Many areas have places where you can recharge an electric vehicle, and this usually takes less than 1 hour. However, rural areas often do not have easily accessible charging stations. In this survey, we will be testing multiple scenarios in order to see which factors are the most relevant when considering purchasing an electric vehicle. We will mainly be testing different policy tools, policy funding, and social norms to understand the key factors that motivate or deter the adoption of electric vehicles. We have also been doing some data analysis and data visualizations from some previous census tract data that we already have. The main significant visualizations and statistics that we have found are charging station distributions, chargers distribution, charging accessibility, and different socioeconomic features to investigate what features will impact people's motivations to buy electric vehicles. We also have some visualizations and statistics about electric vehicle registrations in each region of Florida. So with the future of this project, we aim to essentially use our survey results to draw some conclusions about the adoption of electric vehicles in rural and urban communities. From there, we would like to make a machine learning model to solve one of the barriers with the adoption of electric vehicles. We would like to make a machine learning model to predict where charging stations will be most needed and used in rural communities based on various data points such as travel patterns, vehicle registrations, and geographical information. We would do this using some of the data from our survey results and several other large data sets to identify correlations that can be used when making infrastructure for charging electric vehicles. Therefore, we would use this model to strategically find locations where charging stations would maximize accessibility and convenience for electric vehicle drivers and to encourage the adoption of electric vehicles. So thank you so much.
All right, thank you. All right, our next student presenter is Mason Hagan, who will be presenting Predicting Airline Stock Price Movements with SVMs, Analysis of Load Factor, Quarterly Earnings, and Crude Oil Prices.
Thank you. Again, my name is Mason Hagan. I'm an undergrad. And my research topic, how do I go to? Okay, so my research topic is predicting airline stock price movements using machine learning algorithms. And it's more of a focus on both feature selection and what kind of models work best with trying to determine a relationship between publicly available data and the performance of different airline companies. So actually, what we want to do is draw some meaningful relationship between a lot of publicly available data that's daily, weekly, monthly, and quarterly, and how that affects the health and performance of domestic airline companies. And the domestic airline companies that we chose to work with are American Airlines, Delta, United Airlines, and Southwest Airlines. And we tested different machine learning models, including support vector machines, LSTM, random forest, and gradient boosted machines. So again, our focus was to try to figure out kind of what we're going to use as data, because the most important thing is what data most influences the health and performance of these airline companies. And it actually turns out that there are some pretty interesting factors that go into how airlines do. As we can see, an interesting example that's fairly obvious was COVID, which over the last 3 or 4 years we've seen a lot of, people would say that COVID was an unprecedented event, but there were some fairly obvious reasons why COVID affected airlines. And one of the biggest things was load factor, which is the amount of people who are actually paying customers of an airline, how many people are actually flying on the airline. And it turns out that that data is all publicly available in the form of something called a 10Q and a 10K, which is a quarterly financial statement that is released by an airline company that is publicly traded on their website. All of these airlines have this data on their website. And so what we did was we decided to use data such as that and also other things such as things that might influence their operational costs, like crude oil. If we could get the prices of crude oil and how how economic conditions are influencing where crude oil is headed, then that has a direct effect on how much the airline has to spend on fuel, and hence their operational costs. And if the prices of crude oil are good, then that positively influences the profit of an airline. So our main focus was to kind of focus on what features are most influential to the health of the airline company, and then combine those in such a way that we can create a meaningful prediction for the stock price movement of the airline. So for a literature review, we kind of tried to focus on different general implementations of machine learning models in the context of financial markets, and we found that a lot of people have actually used support vector machines in the past. So initially, this research was going to only focus on support vector machines, but we ended up focusing on multiple different machine learning models because we believe that we want to also focus on not just the individual performance of one model, but also how our features are useful in generating meaningful predictions. So for this first one, exploring the benefits of support vector machines for stock prediction, they actually found a 56% success rate in using a support vector machine for some asset class in, I believe, the New York Stock Exchange. And while 56% may not seem like the most, it's actually highly useful in the context of using machine learning to predict stock price movements, because really anything above 50% is beneficial for any kind of company to generate profit. Here, the second one, they used 3 different machine learning algorithms to predict stock price, and here they also found the most success in support vector machines. The third one, actually, one of our own staff, Alec Kirchable at FSU of the math department, used support vector machines to predict things related to high frequency order book data, which is more in the context of high frequency trading. So outside the scope of just regular equity price prediction, but still using support vector machines, and has some very good high-level overview of the math that goes behind support vector machines. And then I included this thing about sentiment analysis at the end because, again, we're focused more on feature selection, and so we have actually looked at a lot of different options for feature selection, including possibly using daily sentiment analysis on news about travel and airlines. Like, what is the latest news on travel or maybe specific airlines that we're looking at, and is it positive or negative? And can we use that to predict the movement of the stock price? So the process, kind of from beginning to end, was we first are selecting our features, which that is kind of currently the main focus right now, as the project stands right now. And then data collection. We want to make sure that the data that we try to use in our project is reasonably attainable. We can gather data from at least 10 years in the past, and we strongly considered only getting it up to 2019 because COVID is a little bit of an interesting scenario and not necessarily capturing the scope of what we're trying to research. So we tried to focus on data that is available from at least 2009 and before to 2019. And again, that is actually why we believed that quarterly statements that are released by the publicly traded airline companies on their websites was useful, because all of that is available from all of those years that we needed. Model implementation, we again are using support vector machine, gradient boosting machine, long short-term memory, and random forest models, and we're going to feed it all the same data to try to create meaningful predictions, determine the performance, assess the performance of all these models, and then try to figure out which features work best and which model it most accurately predicts the price movement of an airline. And then after that, hopefully we have a working machine learning model that we can use to successfully predict stock prices. And then this is kind of just a synopsis of where we're at right now. And again, we are in kind of the beginning stages of making sure that we find the most meaningful data in terms of how these airline companies are affected. And then we're going to use that in our implementation of the machine learning models. With feature selection, we decided to use crude oil prices because crude oil prices can directly go into the cost of fuel, and which is a huge operational cost for airlines. We decided also to look at some specific technical indicators that are related to the past performance of the airline company that we're looking at. And what we wanted to do was also look at all of the airlines combined, and then create a moving average, a lagging moving average of all of the airline stocks. And then maybe we can use that to determine, okay, if the general performance of all airlines is going down in the stock market. Maybe this is just has not caught up to that trend yet, and it's going to. And maybe we can use that to predict a negative trend in the price of this stock that we're looking at currently. And then finally, previous fiscal quarter's profits. Again, that is available in the fiscal data that's publicly available online. And then for data collection, we are still working on this as we choose what features are correct and what features would best create predictions. But for now, we use the Yahoo Finance API, which is a free API that can be used in Python, to get all of our price data and all of our historical data that goes back up to 10 years and more. And then airline websites, they give the financial statements that we need in order to get quarterly earnings, load factor of every airline, and other data that might be useful. And I believe that is it. So thank you.
All right. So our final presentation for this section is Jonathan Value, who will be presenting preconditioned conjugate gradient method implementation to deep generative modeling.
Sorry.
That's okay.
Wow. Oh my god. I'm like stuck. Drop again. Just like on like a, it's like on like a separate like, PDF.
You're fine. It's on a separate way. What?
It's like not in this, like I just have to go back to like the homepage on there.
Gotcha. So we want to close out of this?
Yeah, we can close out of that.
All right.
So we can close out of this too.
Okay.
Oh, there we go. This one.
This one?
Yeah. I got it.
All right.
Perfect.
Nice. Thank you.
Of course.
All right. Hi, everyone. My name's Jonathan Value. I'm a second-year PhD student in the Applied and Computational Math department. And today I'll be talking about preconditioning a conjugate gradient method for deep generative learning models. So just to start, I want to give some applications, just a little motivation. Earlier, this tied in really well. We talked about imprinting a little bit. So that's one of the example applications that deep generative learning models can do. Basically, it's taking distorted images and we're kind of filling it in with a deep fake in a sense. As well as we also talked about GANs, which, believe it or not, was the second one that I was going to talk about. An application that people do is in drug databases. A lot of times we want to identify different isomers that we can rotate around the chemical compounds in order to detect new drugs. And it can take a lot of time and a lot of effort. So being able to do this utilizing a GANs network on top of the generative learning speeds up the process. So what is a generative learning model? So generative learning models take some type of distribution, in this case a unit Gaussian. We apply the model, which is usually some type of neural network, and we're going to generate a new distribution. So you can think of this by like taking a ball of slime and you're kind of stretching it out. You're creating a new distribution, a new shape there. And how we generally model it is using a normalizing flow first, because we have to put it into math before we can put it into the neural network. So what normalizing flows are, they're invertible mappings between data distributions, so the old one to the new one that we want. And we typically like to design them to be easily computable for the normalizing flow, if we need to calculate the inverse, and if we need to calculate the Jacobian, which is all the different first and second derivatives that we need. And we want to make it expressive, which basically means we want our generated distribution to match what we want our true distribution at the end to be. So in terms of now taking that and putting it into a neural network, in this case, I'm utilizing an input convex neural network. And we're going to kind of just for the brevity of this talk, not go too much into this, but essentially what this network does, the architecture takes an input, y in this case, and like a feed-forward network, we have weights and biases, activation functions are passing through some layers. However, the unique thing with input convex neural networks, first is that we're utilizing convex activation functions here, and secondly, is that we are applying an activation function directly related to the input every time. And the main purpose of utilizing this input is going to come in the training, because what this neural network is going to do, it's going to optimize the distance we need the points in the distribution to travel to make the new distribution. So we want those inputs to travel the least distance possible. So we need to keep track of them. So now putting that all together, how we connect the ICNN to the normalizing flow to degenerative learning models. We basically are going to let this capital F represent our ICNN. We're going to let theta be collections of those weights and biases that we're going to train using the neural network. And there's this known relationship that was produced by Amoshu and Holter that says that our normalizing flow, F, is going to be equivalent to gradient approximations of all the different computations we have to do inside an ICNN, which means we're going to have to compute Hessians in this case, which is going to be very, very costly. So overall, this is kind of the architecture of the neural network. So we have a forward pass where we're estimating log determinant of the Hessian. We'll talk about that in just a second. We're checking, okay, how close are we to our distribution? We're going to estimate the derivatives, do backward propagation, update those weights, find the weights and biases that we want, and then repeat the cycle over and over again until we get an approximate solution to what we want our distribution to look like. So log determinant of the Hessian, the thing that we want to try to minimize for a neural network in our optimization problem here, that basically is going to be how we measure the distance between the input where we started to where we're going. We want to try to minimize that distance like I talked about. So that's a measurement of how we do that. However, we encounter some problems in actually training this network because the Hessian is computationally expensive. We have to compute many, many derivatives. Think about if we have a system that has like 50 variables, then we have to be able to take all the derivatives of those variables with respect to each other, all the different inputs. It can get very computationally expensive. And on top of that, we have to do the derivative as well of that Hessian. So it's unstable. So a solution that was projected by Huang et al. From 2021 is they used what's called a stochastic Lantrose quadrature trace estimator to estimate this value. And then for the derivative, we used this is what's known as the Hutchinson trace estimators. Now, the Hutchinson trace estimator does have an issue because of an inverse Hessian, which again, as I mentioned earlier, we don't really want to compute the inverse of anything. It's a little too hard. So we estimate that using what's known as a conjugate gradient method to solve this V star is replacing this V transpose H inverse inside our estimation for the trace. And the reason why we pick conjugate gradient specifically is because it's what's known as a Krylov subspace method, and it's supposed to converge in n iterations. So if you have, and if you're in n dimension space and variables, say it's like 50, you should converge theoretically in at most 50 iterations then. So here I have a little model, which we'll see. It's okay. Video unfortunately isn't going to play, but basically what happens is this is the input we gave it, which is an input, and this is an experiment done by Huang et al. That I reproduced here. You have the unit Gaussian here, and we made it into 8 small Gaussians, kind of in this ring formation. So what the video would show is kind of all those different points traveling out to create this 8 Gaussian. That's what we're trying to do. So this is what they had. Now, problem with that is that it takes a long time. So we thought that we could speed up the process using what's known as a preconditioner. So convergence of CG is going to depend on the condition number kappa. And if kappa is big, it's going to take a lot of iterations. However, if we can make kappa smaller, we're going to get faster convergence with the CG. So we want to find a way to reduce the condition number. We do that using preconditioning matrices. In this case, we're going to call it M. And we want M to be easily invertible because it's going to add extra computation. And we want it to make the eigenvalue distribution smaller, where eigenvalues are these lambdas.
So by making it smaller, we make the maximum eigenvalue closer to the minimum eigenvalue, which theoretically should make kappa smaller in this case, and therefore reduce the overall iterations that are required. So the preconditioner construction here, we used what's known as a projection subspace method to produce this matrix M here. And essentially what our M is doing is, in this prototypical example, we have the eigenvalues in this case, since it's a diagonal matrix, all the eigenvalues are on the diagonal, so 1,000, 2, 30, 5, 3, 54. And we want to shrink that distribution. So our preconditioner, what it does is we set a threshold for it, and anything that is greater than that threshold is we are just going to shrink right down to 1. So as you can see here, the 1,000, we shrink right to 1, but the 2 didn't meet our threshold, so we keep the 2. However, thinking about the calculations of this, maximum eigenvalue here was 1,000 to 2, so that'd be a condition number of 500. Now maximum is 5 to 1 is our lowest, so condition number of 5. So we have a much smaller condition number. And this translates into our results. So in terms of, this is just a 2 by 2 matrix system, so should take 2 iterations as n iterations for CG. We see that the preconditioner actually doesn't do better than CG. Now, reason for that is because, like we said, we added computational cost. So this means that per iteration, the iterations are going to take more. Where we see the value in preconditioning CG is going to be when we have these larger systems. Here on this graph, we have a graph where the matrix dimension is on the bottom, and we have the number of iterations on our y-axis. So we have 50 going to 4,000. So this is a 50 by 50 matrix going to 4,000 by 4,000. And what we see is that for the preconditioning CG now, with these larger systems, we're staying around 20 iterations. However, beforehand, with the control CG that previously existed, was around 140. So we basically shrunk down the number of iterations by about 1/7 here. So significantly more. Now, each iteration will have slightly more computational time, but as we see here, it's only about double, is about what it is. So really, this would rank around this amount of computation. So it's about 1/4 of the computation that we used to require, and therefore is much faster. So in terms of the expressiveness, because we also want to make sure that these are giving us the same results. Here we have the unit Gaussian again. So this was Huang et al.'s example. And here we have a preconditioned 8 Gaussian that we did. And looks about the same in this case. There are some slight differences because, again, we're using estimations and some stochastics in this. But it gives us equivalently the same expressiveness that we want. And we also tested it on a Swiss roll example here too, which gave us similar results as well, the expressiveness. So what to take away from this? Basically, we see that higher computational expense of a Hessian, as well as higher storage requirements, motivates us to search for approximation methods, such as CG in this case. And preconditioners, such as M, is going to reduce the number of iterations for these higher dimensional systems, but for lower dimensional systems, it's still okay just to use CG. And in this case, we get the same expressiveness. And some possible future explorations with this, there's what's known as a Hutchinson ++ trace estimator, which theoretically should speed up this estimation even faster, as well as other preconditioner constructions that are out there. There's always better preconditioners that we can find here. And in addition to this, I also do some work on neural networks, and also I've just gotten into doing some Navier-Stokes work as well. I want to have a few acknowledgments here. I want to thank my collaborators who worked with me on this project, Lauren Proctor, Edward Schau, and Stephen Stern. I want to thank Florida University and FSU Libraries for having me here today. I want to thank the people who funded and gave us the resources for this, which was the NSF and then the Embry University Department of Mathematics. The advisor on the project, which was Dr. Ren Ji, and 2 postdocs who helped with the project as well, Dr. Huan He and Dr. Yuling Shi. All right, here are all my references, and thank you so much.
All right, thank you very much. Those were all really great presentations. So we have a few minutes. If anybody has any questions for any of our student speakers, please feel free to jump in. Let us know who you're asking. Yeah.
I'll start with go with Madalena, right, for your deepfake presentation. So I think a lot of what you were focusing on was static images, right? So I mean, I probably see it like every day online, like some new like AI image or something, and oftentimes now in its current state, like you can zoom in on a lot of them and find like those artifacts you're talking about with like people have like 6 fingers or they're like missing a thumb or something like that. Eye movement you mentioned can typically be pretty weird. So it seems like your guys' kind of analysis and the thing you're moving forward with will be effective at identifying that. But how do you think we'll be able to keep up with the evolution of it to when those artifacts are no longer, you know, as visible even to the human eye, and you know, from there probably they'll develop techniques to curb any attempt at analysis for it too.
Yeah, well, there's really no way of saying, but I think like from a programmer's perspective, I think a lot of these algorithms, the more you feed them, the better they get. And eventually I do think, you know, with time, they're just gonna have so much information already built into them that they'll just analyze it already.
Yeah.
So we might not detect it with the human eye, but they'll just have so much input that they will.
Thank you.
So.
I'm just gonna keep shooting. I wrote down a lot of questions. I'll do Sahil for fantasy football. That was cool. I enjoyed that because my team sucked this year. What about using in the future like more like qualitative input features? You know, like player age, injury history. You know, like how long they've been in the NFL. And any other factors like that, do you see, you know, that is something that you could move forward with potentially?
Well, my line of thinking is that ESPN, they already have people who have spent years working on models that likely already incorporate this data.
Okay.
And for me to individually say that my model would be better than ESPN's would likely be inaccurate. It would likely take me much longer and work with a lot of more people to actually create a model that would even rival ESPN. So my idea is that I should take ESPN's projections and take ESPN's model and maximize the value output that I can obtain from that model instead of trying to create my own and trying to beat the pros and experts who like they have all PhDs in the field and have worked for years on the model.
Okay, yeah, interesting. How was this year especially, like there was, you know, probably 5, you know, NFL players in the top of the draft that were picked 1 to 5, unless somebody was really stupid. Like Justin Jefferson was picked first in every league. So how is this kind of different than like almost the auto draft feature, right? Where it'll like fill in, you know, the next best position with the next best player, you know, in that position.
So auto draft basically drafts from highest projected value. I don't think it really drafts for a specific position.
Yeah.
So like let's say you already have 2 running backs drafted. If you need a wide receiver, if the best player available is a running back, they might still draft a running back. It's not very smart in its analysis. It's not going to auto draft is likely not going to win you leagues. What we can do with my data is we can actually take into account positional need, and it can take into account where everyone else is drafting as well. Whereas auto draft will just say this is best player available. It's like in the NFL draft, if teams need a certain position, they won't always draft best player available, especially toward the bottom tier of the draft. They draft for need, and that's what my model accounts for. That auto draft does.
Cool. And last question for you, just what tech stack were you using for this? How did you implement it?
So what tech stack?
Tech stack.
Well, what do you mean?
Like, were you using like Python for it?
Yeah, I was
what
using
libraries?
So I was using Python. I used Pandas for most of it. I used like Beautiful Soup to download the data from ESPN. Someone had actually scraped out all the ESPN projections themselves, so it was very easy to just scrape in. And then for the models, I just used Beautiful Soup. Took the models in, and then in terms of just simulation, those were just like hard-coded simulations with like Pandas, where I just used for loops.
And did you take the data from the mock drafts that you did as well? You just like input it in there?
Yeah, so it was, so I could just like copy paste the HTML into a text file, and I had code that parsed the HTML file and added up the projected points.
Awesome. Show me your teams after this.
I had a question for Reagan. Do you see, are there any regions or cities that you see like moving in the right direction with kind of some of the implementations that you've recommended?
Yeah,
Or-
so from what I've like read about, it seems like California definitely has like the most, like from a legal perspective, they have like a bunch of different like financial incentives that they've put into place, and I feel like they've made a lot of like good moves going in the right direction. So yeah, definitely California, probably the best, and then probably like New York is up there too.
Gotcha, thank you.
And you were focusing specifically on like rural communities, right?
Yeah, I know it's kind of like hard to say. Over
I
and
know,
over
it's the
again.
worst.
Yeah, we're mainly focusing on rural communities because I feel like that's where there's kind of like the most room to grow.
Mhm.
Awesome. All right. All right, if there are no other questions, let's thank our student speakers again. All right, and then I'll just briefly close this out here. So I would like to thank everyone here for attending our Empowering Minds through Data Science and Machine Learning Symposium. We've heard some really great presentations, I think, that represent sort of the variety of research that's happening at FSU around machine learning, artificial intelligence, and data science. And as we've seen today, there are many applications for these technologies, which will affect our lives in many ways. We have seen this within academia and within popular culture as well. And I think having these type of conversations like we had today are only going to increase in importance sort of as time moves on and we see more and more of these models come out. I'd like to again thank several people who made the symposium possible. I'd like to thank Dr. Jinping Zhang, our keynote speaker, and our student presenters for taking the time to share their work with us today. I would like to thank all of our libraries colleagues for all of their support in getting this set up and running. I would like to recognize Reagan, who did a lot of the coordination for the event and brought all of our speakers in and put the program together. And then finally, thank everyone else who I might have missed that assisted with the event today. And then finally, all of you for coming and participating in the conversation with us today. And with that, I'll ask once I'm done, all of our presenters to stick around for just a second. I have something for you. But otherwise, thank you all so much. We still have plenty of refreshments over there. Please feel free to take some. And please feel free to stick around a little bit if you want to chat with each other, network, have conversations. All right, thank you very much.